Hello dear friends, and welcome to this new session in which we will be building custom losses and metrics. The first method we'll look at is building a custom loss method without parameters, the next with parameters, and finally we'll build a custom loss class. And then from here we'll go on to build custom metric method with parameters, custom metric method without parameters, and custom metric classes. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. Most times when building models and training them, all you need to do is to pick this loss function from one of these losses available in the documentation. Now, in a case where you have to build a loss function from scratch or a custom loss function in which defining the loss isn't as easy as just specifying this loss function name right here. So right now let's look at how to build such custom loss functions. Here we're gonna have this custom binary let's call it custom BCE. BCE stands for binary cross entropy. So we have the custom BCE loss right here, and then we'll define it just above this cell. Now we have our custom BCE loss. There we go. And here, what we're gonna do is we'll define this BCE object, the binary cross entropy loss object, and obviously here we have binary cross entropy. There we go. So we've defined this object of this class, and then we return this computation of the binary cross entropy of the y true and the y pred. So here this y true is the actual output labels, and here's what the model predicts. You could understand this better by taking a look at the documentation, where here you see to define this object, and then in computing this binary cross entropy loss, you see specify this y true and y pred right here. Now this binary cross entropy could take several arguments, for example from logits, label smoothing, the axis, reduction, and the name. So that's it. We have this custom binary cross entropy, and just here all we need to do is to specify this name. So let's take this off and we're fine. Okay, now we just run this. We run this binary cross entropy. We run this. Metrics not defined. Let's run this cell, and then finally run the training. We get this error. This function takes 0 positional arguments, but 2 were given, so we have to have this here y true and y predicted. Okay, we run that and run that. We could see here how this training process looks similar to what we've had already when we're dealing with the preconceived binary cross entropy loss. Now that said, let's suppose that we are going to pass in a parameter here. So we want to parameterize the way in which we calculate this binary cross entropy. That is, we want to have this binary cross entropy multiplied by a given factor. Let's say we want to multiply this by a factor of, say, 0.5. In that case, we could have this here as a factor, and then we'll pass in this factor right here. So we pass this in. Let's stop the training, and then we train to see how that works. We run this here and run this. Factor not defined. We could include this factor here. We run it. Factor still not defined, and this brings us to the way in which we'll define models, or rather define loss functions in which we have a given parameter. So right here we're gonna define a loss here, a loss function, and then we pass in our y true, y pred. So it's going to be like similar to what we had with a custom BCE without a factor. We have that, and then in here we have this BCE, and then we return this right here. Now notice how we take this 2 off. So we having just this factor, and that's what we're going to be passing here. And then here what we return is this loss method right here. So we define this custom binary cross entropy. We return this loss method, and this loss method we take in the y true, the y pred, and we carry out the computation as we had done before. But now note that we're multiplying this by a given factor. So here we could define our factor. Let's have this factor and here factor. Then before this, we'll define this factor. Let's take this factor to be equal 1, because in our case it's actually equal 1. But supposing you are having a different problem, you may want to modify this parameter as you wish. Let's have this factor here. That's fine. Now let's rerun this, and hopefully we should have no error. So that's it. We have no error. That seems fine. And then we run our training. As you can see, the training process continues normally. And we could now check out on another method of building custom loss functions, which is that of actually building a loss class, which inherits from the Keras loss class. So that said, let's add this here. And then we have our class. We'll call this custom BCE. And then we'll inherit from Keras losses loss. Okay, so that's it. Now once we have this right, we have our init method, and just like we did here, we're going to pass in a factor. So let's have this factor. Then we inherit methods from the parent class. There we go. We have our custom BCE, and that's it. Okay, so we have this right, and then we now go straight forward to creating this factor variable and take this value factor, and that's it for the init method. From here, we're going to define a call method where those operations are going to be carried out. Now here we have this call method, and then what we take in is yTrue and then yPred. Okay, so we've taken this. We now do exactly the same thing we did here. We could copy this out and paste it right here. We have our BCE defined, operation carried out, and here we have self.factor. Okay, so everything looks fine. We have our custom BCE defined, invalid syntax. There should be a dot just right here. We run that again. That's fine. Okay, so we have that right, and what we do now is take this off. So here we have custom BCE, which is this class we had defined, or we just defined right here. Okay, now we should also note that you could pass in the factor here. We actually have to pass in the factor. That's it, because we didn't specify a default value, so we have to pass that. Now let's run this. That's fine, and then we rerun our training and make sure everything works well. We get in this error. The call takes 2 positional arguments, but 3 were given. Let's get back to this, and we see this error. We did not put in the self. Okay, so that's it, and let's rerun this. As you can see, the training went unsuccessfully. Now we know how to build custom loss functions with TensorFlow. We then move on to building this custom metrics, just similar to the way we did with a loss. So here we have a custom metric. We'll start with a custom method, so we'll take this off, and then just right here we have custom metric. Let's add this and this. We paste this out here and have custom accuracy. We now get back to the documentation, TensorFlow Keras, and then metrics. So right here you would have this accuracy which has been defined. Here we go, we have binary accuracy. So that's it. We have the binary accuracy. We specify yTrue, yPred, and the threshold. There we go. We can paste this out here. This is the loss. Let's go back up to this metric. Okay, let's paste it out here. So now we have this accuracy which takes in the yTrue and yPred. So we just return, we basically return this. We return binary accuracy which takes in yTrue and yPred. Okay, so let's take this off, and that looks fine. Now we have our custom accuracy. We run this as well. We get to this compile, custom accuracy, fine. We compile a model and we train the model. Everything looks good. You could see this custom accuracy. Now, let's suppose we had a factor. We're gonna use this same kind of approach we had with the loss method. So we just simply copy this out, and then right here, we have this paste that. Then we have our custom metric right here. Here again, we have custom accuracy. We're taking a factor. We have this metric, which changes to metric. There we go. And then we simply have this. So let's just copy this out and paste right here. So here we have this here. Let's copy this out. Okay, so we have this, and we now multiply this by the factor.
So here again we call on the metric method, and that's fine. We run that. We have this custom accuracy. Oh, okay, we haven't stopped this training yet, so let's stop this training. That's fine. We get back here and run this. Looks good. Compile and train a model. We're told this takes one positional argument, but two are given. So let's get back to this and then include this factor. Run that, and the training looks fine. We can see our metric right here. Our next approach will be the class-based approach, similar to what we did with the loss. So here we have this custom loss class. We'll build a custom metric class. Let's add this and add this code. So we have that, and then we have our custom metric class. This class here is a subclass of the class metric. We have our class metric, and then just right here we have custom accuracy. So we have this custom accuracy, and then yeah, we will specify the name. Let's have this name. Let's say we want to put here custom accuracy. Okay, and then we pass the factor to, which by default we set to 1. So that's it. Now we have custom accuracy. We have our factor, and then what we do is define this accuracy by calling on the add weight method, which comes with this metric class right here. So we have this add weight, and then we specify the name, which is the name we've passed. We have the initializer equals zeros. So that's it. You'll notice that this will look slightly different from what we saw with the custom loss. As unlike with the loss class, which has this call method, here would instead use 3 other different methods. The first we'll be looking at will be the update state method. We have update state, then next we'll have result method, and then the reset method. So we have this reset right here. The update state method here permits us update our metric state. The result permits us to output the metric values, and then the reset permits us reset the metric states. So we have here reset states. Here we go. We start with this update state method. In this update state, we're going to be assigning a value to this accuracy variable. So just right here we have self.accuracy. We assign a given value. Now the value we're going to assign is exactly the same we had here with this binary accuracy. So let's take this factor and then paste out here. We paste it here. Okay, so this is self.factor. That's fine. So that's it. We assign this value to this accuracy variable. This method too takes in the y true, the y pred, and then with the result we have a return. So here we have this return self.accuracy. That's it. And then here for the reset states, we are going to reset the state at the end of each epoch. So once we finish with one epoch, we reset the state and then recompute or re-update the state and then output this result. So here again we have self.accuracy, assign the value 0. That's fine. Let's run the cell. We get this error because this is actually metrics. So let's take this off. We have here metrics. We run that again. They should be fine. Okay, so we have our custom accuracy built. We now get into this here. So let's take this off now and specify our custom accuracy. Then here we specify the name. But anyway, we've gotten default value, so we could just pass it this way. Let's run the cell and then we restart the training again. We get this error. Update state got an unexpected keyword argument sample weight. Now we get in this error because here we didn't put the sample weight as one of our arguments. So here we should have the sample weight. We're not going to be using that, so we'll just set it to none. Let's run this again. Fine. We recompile and then train our model. We get this other error. The input y of equal up has type float 32. That doesn't match type 64 of argument x. So this is actually an error which comes up because right here when computing this binary accuracy, we have y true and y pred of different data types. So let's print this out and you could see that y true, and then y pred. We run this again, looks fine. We get down to this here, this compilation. Recall, when we want to debug, we could run eagerly. So let's run eagerly, set that to true, and that's fine. We run this again and try to understand what's going on. So as you could see, that's exactly what we expected. We have this int 64, so this is an int and this is a float 32. We have the y true, so we could cast this here. So let's cast this value, tf.cast, and then we specify the d type to float 32. Float 32, that's fine. And then just here we take this off. Okay, so we run this again. There we go. We now compile and then train. We get this other error, cannot assign value to variable custom accuracy. The variable shape and the assigned value shape aren't compatible. We get back to this here, and what we do is we're gonna print out this output which we assign to the accuracy. Here we define this output, and then we simply take this out from here and have this as our output, and now we're gonna assign this output. So since we now have the output, we could print it out so we understand exactly what we're assigning to the accuracy. Let's run this cell, that's fine, and then we get to this compile and train the model. Okay, there we go. So now we see exactly what we're assigning, but you'll notice that instead of just assigning a single value, we are assigning this list, and this is the reason why we were getting that error. To solve this problem, we would also have to understand that this output actually corresponds to whether the model's prediction was correct or not for each and every element of the batch. So when we have a 1 like this, it means the prediction was correct, or the model's prediction was correct, and 1 and so on and so forth. So because we've trained a model for quite a while, you see that for all this, or for this particular batch, we have kind of like 100% accuracy. So instead of printing out 100%, what the model gives out is this list. Now let's look at this again. We see now that with this other batch, we have some zeros. So out of 32, we've had 3 zeros, and hence our accuracy in this case is 90% for this batch. That said, we have to figure out a way of counting the total number of ones and then dividing by the total, or by this length, which in this case is 32, or by the batch size, which is 32, and then multiplying by 100, or we could just let it like that. So we'll make use of this method, count non-zero, where here we could count the number of non-zeros values very easily by just calling it, and that will be fine. So let's copy this here, and then instead of having this output, we'll count the number of non-zeros. There we go, we count that, and then we divide by the length of this output. So we divide by the length of the output, but this length is gonna be an int, so we're gonna cast this so we get a float. We have that, and then d type equal tf float 32. Looks fine. Okay, so now we have that, and then let's take off this output and then rerun again. We then compile and then train the model. We still get another error. So what we'll do is we're gonna just check in the documentation, and then here, what do we see? We see that by default this is an int. So here we could also cast this. We cast this into a float. There we go. We have this output. We don't really need to cast that because we could specify the data type. So here we have the output, and then d type equal tf float 32. Okay, so that's it. Hopefully this should be okay now. We compile the model, start the training, and everything looks okay now. We could now stop this and then get back to graph mode. So let's run again so that we could now train even faster. And that's it for the section. We've seen how to build custom losses and metrics. Thank you for getting right up to this point, and see you next time.